Welcome back everyone. In this lesson we are going to learn about another extension of Gaussian elimination method, which is known as Gauss-Jordan method. So let's dive into the details of this method. So if you remember the Gaussian elimination method, the naive one or the complete one, whatever it is, from the previous two lessons, you remember that we convert the original coefficient matrix into an upper triangular matrix. Okay, so that's the first step of the Gaussian elimination method. But in Gauss-Jordan method, we convert the original coefficient matrix into an identity matrix. Okay, so identity matrix and all the diagonal elements will represent the unknown variables. So that's the difference between the Gaussian elimination and the Gauss-Jordan method. In the first case, Gaussian elimination method, we convert the coefficient matrix into an upper triangular matrix. But in the Gauss-Jordan method, we convert the coefficient matrix into an identity matrix. Okay, so what is the difference here? If we if we see that we do not eliminate all the terms below the principal diagonal. We not just eliminate all the diagonals, all the elements below the diagonal, but we also eliminate the elements above the principal diagonal. As a result, except the principal diagonal, all the elements of the matrix will be zero, will be vanished. And that's the difference between the Gauss-Jordan method and the Gaussian elimination method. So if we see an example of the Gauss-Jordan method, it will be very much clear to you. It's very much the same as the Gaussian elimination method, but there's a slight difference between the calculations. So in this case, we are going to use the augmented matrix. Okay, a new term. This is the augmented matrix. So what is an augmented matrix? You remember we construct the coefficient matrix using the coefficients of all the unknown terms. Okay, but in augmented matrix we incorporate a fourth column or another column which is the values of the constant terms on the right hand side of the equations. So using these values, all the coefficients and the constant terms on the right hand side, if we want to construct the augmented matrix, it will something look like this. Okay, this is the original equation, original system. In the first three columns we have the coefficients of the unknown terms on the left hand side of the equations, and on the last column we have the constant terms which are situated on the right hand side of the equations. Okay, so this is an augmented matrix. We also incorporate the constant terms from the right hand side of the equations. Next, we normalize the first row by dividing the pivot element 3. Okay, so what is this? We want to normalize. So in this step was not present in the Gaussian elimination method. So after constructing the augmented matrix, okay, after constructing the augmented matrix, we divide the first row by the pivot element 3, and then look at this. What is the result? The first equation becomes modified something like this. Okay, 1 minus 0.33, which is due to the division of minus 0.1 divided by 3, then this term which is minus 0.2 divided by 3, and this the last term which is 7.85 divided by 3. So as a result, the first equation becomes something like this. The second and third one remains the same. So what we want to do, we want to eliminate these two terms. Okay, if you remember, to construct an identical matrix, we need to remove the elements that are below and above the principal diagonal. Remember, whenever we are considering the principal diagonal, we are just consisting the principal diagonal from the first three columns. The last column is not considered here. Okay, the principal diagonal is this 1, 7 and 10. The last column is not considered to calculate for the principal diagonal. So what we want to do, we first remove these two values, 0.1 and 0.3. That we also used the same approach in the Gaussian elimination method. So how do we eliminate this 0.1? We just multiply the first equation by 0.1 and then subtract the result from the second equation. Okay, so look at this. If we multiply the first equation by 0.1, what we'll get? 1 into 0.1, which is 0.1. Then multiply this minus 0.3033 with 0.1, then this term with 0.1 and this term with 0.1. So the first term, the first row will be changed, and then we subtract the first row from the second row. As a result, we will see that the first two elements will be same. As a result, due to the subtraction, these second element will become 0. Okay, and this is the result of the subtraction. So if you carefully notice that we have said that we normalize the equation by dividing by the pivot element 3. This is the same that we actually used in the Gaussian elimination method. In that case, we just multiplied the first equation by 0.1 divided by 3. So in this case, we are just dividing the step into two separate substeps. Okay, so that is actually the same that we used in the Gaussian elimination method. We are just using a special term here, normalizing, but that is not that was also present in the Gaussian elimination method. So in this way, in the similar way, we can eliminate the 0.3 term. How we do that? We multiply this term, the first row, with 0.3, and then we subtract the result from the third equation, and we will get this equation. So let's see what we have got so far. We have eliminated the first two terms under the principal diagonal, and we need to go further to make the diagonal elements to make the off diagonal elements 0. Okay, now what we got in the next step, we need to eliminate this term, that means minus 0.19, which is under the principal diagonal. So similarly, we now in the second step, with the pivot coefficient is 7.033, which is the second coefficient. When we normalize the second row by this pivot coefficient, that means we divide all the elements of the second row by this pivot coefficient, and as a result, this term will become 1. And then we multiply the second row by minus 0.19. As a result, the first term, this term, that means this diagonal element term, will become minus 0.19, and then we subtract the whole second row from the third row. As a result, this term, which is 0, which is under the principal diagonal, will become 0. Okay. Also, since we are using the Gauss-Jordan method, we need to eliminate all the off-diagonal elements. That means we need to eliminate this term. That means minus 0.033. This is also an off-diagonal element. Okay. So how we are going to find that? We are just going to multiply the second term by this minus 0.0333 term, and then subtract the result from the and then subtract the second row from the first equation. As a result, this term will become 0. Okay, so in this way we just eliminate all the off diagonal elements. Okay, now let's turn to the third row. That means since now we have eliminated all these off diagonal elements, we have made this 0. Now we need to eliminate these two terms. Okay, the diagonal elements here are going to be 1, and the off diagonal elements are going to be 0. Now the off diagonal elements that have not yet vanished are these two terms. So how we are going to eliminate this? We are just going to normalize the third equation by the pivot coefficient. Now the pivot coefficient is 10.0120. So we normalize the third equation, and then we multiply the third equation by this minus 0.04188848, and then subtract the result from the second equation, and if we substitute the second equation with the result, we will see that the second this off diagonal element will become 0. Similarly, we multiply the third equation by minus 0.06802629 and then subtract the result from the first equation, and we will get that this term will become 0. So look at this. In all of the previous calculations, we have just considered the first three columns to consider our diagonal elements or off diagonal elements. We are not considering the last columns. So in all the calculations, the last column is automatically changed due to the numerical division or multiplication or subtraction. It is automatically changed. We do not need to consider this. Now let's see what we have. We originally had a augmented matrix. Now we have a modified augmented matrix. Look at this. The first three columns, this is an identity matrix, and this is the B constant, modified B constants. So if you remember, the first row was x1, x2, x3. Now since these two terms are 0, that means in the first row we have only the x1 term. That means x1 equal to 3. Then here we have x2 equal to minus 2.5. Then here we have x3 equal to 7. So that means we have just finally got our result x1, x2, x3 directly from the matrix. We do not need a second step which we used in the Gaussian elimination method, which is known as the back substitution method. So in Gauss-Jordan elimination method, we do not need the back substitution step because we already got the final results. So that's the benefit of Gauss-Jordan method. We do not need to use the back substitution step. Okay. So from the modified augmented matrix, the first three columns are going to be the coefficient matrix and the last column is going to be a constant matrix. And if you just modify this into the standard notation, that means the constant matrix multiplied by the unknown vector equal to the B constant. So if you just multiply this, the first row will get just x1, x2, x3. So sorry, this note, there is a problem here. This one should be x2. Okay, so x1 equal to 3, x2 equal to minus 2.5 and x3 equal to 7. So please try to change this notation to x2. So in this way we can use the Gauss-Jordan method. We have seen that it has certain benefits over the Gaussian elimination method. Unlike Gaussian elimination method, we do not need to use the back substitution method. As a result, this is a plus point for our Gauss-Jordan method. So in this lesson we have learned about Gauss-Jordan method. We have seen how this Gauss-Jordan method is implemented in the practical scenario. So please try out the MATLAB code with this attached with this lesson, which implements the Gauss-Jordan method. So please go through the details of the code so that you can understand how the elimination of the off diagonal elements are completed. So in the next lesson we are going to learn about another method which is used for solving a linear system, which is matrix inversion. And I guess you already know how to invert a matrix. So that's the main criteria of matrix inversion method. So it's a very small method, and it is very small. It will be a small lesson. So till then, thank you so much.